Let's look at a problem where you're calculating shear forces in a bolt pattern which is carrying a torsional load that in a case where the bolt pattern is not symmetric. So this problem, which stated as 3 here, is symmetric as drawn, so its centroid would be equidistant between the centroid and all of the bolts, which would mean the resultant shear forces would be equal as well. They'd be in different directions, but the magnitude would be equal. The problem 4 here assumes that bolt D is taken out of consideration, so that leaves a triangular bolt pattern whose centroid is going to be up here somewhere. Now in this case, the distance to locations A, B, and C are all unique. That does add to the steps to calculate those values just a little bit. So in the solution, I start with just a sketch, free body sketch of the resultant situation, where I've got each bolt identified and I've located the centroid and calculated the radial distances from the centroid to each bolt. Those radial distances along with the angles I'm using, I actually just used a SolidWorks sketch to figure those out, but you could do it with a bit of trig as well. Let's see, another assumption here is that the vertical shear is evenly carried by all 3 bolts. So we're left to figure out what the shear due to the moment is, which that force I'm calling here FMA, FMB, and FMC. Now in the end, each of those forces is going to create or counter part of this moment. And that's going to just be FMA times RA plus FMB times RB plus FMC times RC is going to be equal to this value. But FM, A, B, and C are not equal to each other, so we have 3 unknowns. So we have to have some scheme to equate FM's A, B, and C, and what's being done here is, or what's being used here is proportionality. So we're assuming the plate is rigid, so that as it rotates about this centroid, the plate doesn't deform itself, which means that each bolt is just going to be moved or sheared by a proportional distance. That also means is that bolts which are farther away are going to take a larger shear force for that to be true. And we can just use proportionality of the radial distances to figure out how much larger or smaller one force is in relation to another. So what I've got in these expressions here for FMC and FMB, up top here, 2.61, that's RC. That's the distance out to location C. And on the bottom, 1.46, that's the distance to bolt A, RA. So I've got RC over RA times FMA is equal to FMC. So that gives me an expression for FMC in terms of FMA. Do the same thing for FMB, where we have RB divided by RA times FMA. This should be an A right here. And there we go. So now I've got FMC and FMB in terms of FMA. So when I write out the summation of moments about the centroid, FMB, FMC, and then I substitute in the expressions that I just came up with above here, I now only have the one unknown and I can solve for FMA. Once I have FMA, I can plug that into these 2 expressions here and solve for FMB and FMC. So those are the shear forces due to the torsion, the twisting of the bolt pattern. We still have the shear force due to the direct reaction, 425 at each bolt. So to get the true totals, we need a little bit of vector addition. I'm not going to go through the steps for this. This is standard vector addition, but I will leave you with the results here to check out.